My name is Subhankar Pal. I'm a research scientist at IBM T.J. Watson Research Center, working on accelerating homomorphic encryption, amongst other things. I'm a computer architect by training, so I'm still trying to catch up in the space of homomorphic encryption. But every day I learn a bit more than yesterday. So let's get started with the talk. So this is sufficient pruning for machine learning and homomorphic encryption. It's joint work between IBM Watson and our colleagues at IBM Research Israel. So I want to thank them for their contributions, and with that, we'll get going. So what I'm going to focus on today is privacy preserving machine learning, or PPML, using FHE. FHE needs no introduction for this crowd. It's a method of computing on homomorphic encrypted data. So particularly for PPML, which is a big use case, the model and/or the input data can be both made private. So let's take a look at an example of detecting COVID-19 from a patient's X-ray image. So let's say a hospital is the client and sending the patient's private data to the server for encrypted inference. So that can be done using FHE by encrypting it, sending it to the server via a secure channel, and then running an encrypted prediction on it. And the result is sent back to the client for decryption, and in this case, unfortunately, it turns out to be COVID. That's the typical workflow. As we know, FHE operations are expensive, so to do something like an element-wise multiplication in plain text format, you would just have a data flow graph representation that looks like this. In FHE, in particular with CKKS, you would have something that looks like this, which is monstrosity. And that this itself gives you the idea that there's several orders of magnitude slowdown compared to plain text operations. And this is the motivation to do both hardware and software co-design techniques to try and bridge this gap. So the main idea we started to look at is how to do pruning for neural nets under homomorphic encryption, and whether techniques we have learned in pruning for the space of plain text neural networks work. So in the plain text domains, we can do a typical pruning process, which involves, let's say, pruning weights and neurons. The pruning weights can be based on an absolute threshold, such as the L1 norm of the weight values, and neurons can be based on some similar metric, or we can do it randomly, and there are various combinations of these methods. So an illustration is shown on the right side. So we have a 3-layered network, and we're going to prune it, so we can just remove some nodes and some edges, and it could look like this. It's a very common technique in machine learning domain in plain text machine learning. It helps to improve latency by reducing the number of operations, as well as the storage cost, because you don't have to store the weights that have been pruned away. Certain FHE schemes now, like CKKS, which is going to be the focus of this talk, support homomorphic encryption using a technique called single instruction multiple data, or SIMD. So the idea is to pack a lot of data into the same ciphertext message, and we say that it consists of SIMD slots, and the same operation is applied to every slot in the ciphertext. So to illustrate that, here you have a set of 5 numbers encrypted into the same message. You can add it to another message to get a bunch of results that are also packed into the same message. That is the SIMD style of computation. Now I'll show that the problem that arises is when you prune the ciphertext values. So if you have this ciphertext again and you prune away a couple of values, the problem here is that there's no point of this pruning, because you still have to encode and encrypt this message into a ciphertext, which after the encryption process does not have any zeros in it. So really there is no saving done from pruning the individual values. What we're going to look at is a method of generically packing values into schemes that support SIMD. And how do we figure out how to fix the problem of pruning for this context. So in general, word-wise FHE schemes like BGB, BFP, CKKS, and there may be others support the SIMD style of computation. And as I mentioned, the encryption is done on a plain text vector into a ciphertext message, and then the operations are performed slot-wise. So we took this work called HE layers, and the references are shown in the bottom. HE layers is a framework around a method called tile tensor that packs various tensors like matrices and vectors and 3D tensors into tiles, which are the fixed size chunks that each get encrypted into a separate ciphertext message. And to show an illustration here, we have a plain text matrix of shape 2 by 6. And if we run it through HE layers, it's going to give us a tensor where the packing is shown here. So each ciphertext has a pre-specified shape. In this case, just for illustration, it's 2 by 4 by 2. So the idea is, how do we pack a matrix of shape 2 by 6 into a ciphertext of 2 by 4 by 2? It's done by dissecting the matrix in this form. And then you can see that because the length is not divisible by the length of the ciphertext, there is some zero padding added. And then we also see that there's a 3-dimensional extension, and those are replications of the plain text values. And the replications are required in order to do batch processing. So if you're doing inference on a batch of images instead of a single image, that's when the replications are required. So the volume of the ciphertext is equal to n over 2 in case of CKKS. And therefore, the depth kind of compensates for the X and Y dimensions of the ciphertext. And we need to remember this for future slides. That means that the bigger your X and Y dimensions are, the fewer your replications along the Z dimension is, and therefore the smaller number of images you can process using it. So if you have just one image and you want to do inference, then you don't really need too many replications. Otherwise, it's just a waste of memory. And we'll touch upon this point in a future slide. Okay, so combining this slide with what we learned in the previous slide, the first insight is that what matters for neural network inference under FHE is not individual sparsity. So it's more about tile sparsity, which is the percentage of tiles or ciphertexts that are entirely zeros. And those are the ones we can completely discard. If you have zeros in combination with non-zeros within a ciphertext message, then there's no point of having those zeros. That's the key point we need to remember. Okay, so let's look at how things would work out if we just prune and then pack using the method shown in the previous slide. So let's take a different example now. It's a 4 by 6 weight matrix with these values, and the bottom just shows a neural network representation of this weight matrix. So it's a fully connected layer. Let's say we prune the weight matrix with a threshold of 1. So it removes out a bunch of values, makes them zeros. And now if we were to pack them as is, the packing would look like this. Consider 2 by 2 tiles just for illustration. And let's ignore the replicated third dimension for now to keep things simple. So we can see that there's just one tile that has all zeros. So in essence, you can only reduce 1 out of the 8 ciphertext messages if you just do a prune and a pack. So we realized that we can do better. So instead, consider that you don't pack after pruning. Instead, after pruning, you apply a step called permute. And what you do is just permute the rows and the columns in a certain way. And that's shown using the rows and the columns, the row and column indices on the left and the top here. And by doing this certain permutation followed by packing, we can increase the number of zero tiles significantly. So in this little example, by doing this particular permutation, we can get up to 4 out of 8 ciphertexts to be all zeros, and we can throw them away. So how do we do this permutation? That's the next logical question. If you were to do it exhaustively, it gets really difficult because for an m by n matrix, the complexity is order of m factorial times n factorial, and that gets really prohibitively large for any decently sized weight tensor in a neural network. So instead, we propose to do it in an iterative manner, and I'll explain that in the next slide. Okay, so let's take the weight matrix. This algorithm is going to illustrate the permutation, which is done iteratively. So we'll take the weight matrix and split it into row vectors first. Note that if we pack at this point, it's just showing that it's going to give us 1, 0 tile, so we're not going to do that. Instead, we would run it through a clustering algorithm. So we experimented with a few things. Turns out k-means was decently good for us. So we're going to treat each row as a vector to feed into the k-means algorithm with k set to m by t1, which is the height of the matrix over the height of the tiles. And then after the k-means, we get a shuffled set of data points. So it's really clustering based on trying to get all the zeros together at a high level. And if we pack the matrix at this point, we would get 2 0 tiles, which is still not ideal. So what we can do is do this repeatedly after transposition in the middle. So we transpose and we run it through again. This time the dimensions of the or the parameters of k change. But it gives you a similar shuffle for the columns now. And if we transpose it back, turns out for this little example, we have arrived at the optimal number of 0 tiles after just 2 iterations. So here it's 4 out of 8 0 tiles. But for larger matrices, we keep doing it iteratively until some convergence criteria is reached. Okay, so some details are, so the k-means treats each row as a data point. So we need to define a distance function for the k-means algorithm. So we constructed something called grouped Hamming distance. So if there are 2 points in the k-means space, ai and bi, we would first quantize them. So any non-zeros become ones and any zeros remain zeros. And then we do an AND, so AND of AI and BI. And then we look at how many groups of a certain size are non-zeros. And that count gives us the distance. So again, just to reiterate, what this distance function does is it tries to cluster groups of zeros together where the group size is dependent on the tile size, which is the ciphertext message size. Yeah, and then we have to also implement a balancing scheme because you don't want to have too many points in one cluster. For example, if you had lots of rows with the first 6 elements being zeros, you don't want all of them to cluster together. You would still want to cluster them based on the height of each tile. So we also implemented a balancing scheme that reassigns points from centroids that have too many points in them into the next best centroid as part of the k-means algorithm. Okay, so we have an idea now of how to do the permutation for a single fully connected layer, which is a single weight matrix. We just alternately apply our permutation algorithm to the rows and columns. So a bigger picture view would look like this. So you have the layer and the weight representation of it, or sorry, matrix representation of it. And then you permute the rows and columns, and then you just repeat it until convergence. Now, the nuance here is that for correctness, we also need to introduce an input permutation matrix PI and an output permutation matrix PO for the input and output activations. And that would look something like this, because the idea is because you have reordered the weights, you also have to reorder the inputs that arrive into that layer. And that's just shown pictorially here. So The second problem we came across is if we just extend the scheme naively to a multi-layered neural network, it's not scalable. In fact, it's worse performing than the baseline unpruned network. And that's because after every layer of the network, we have to introduce this permutation layer. So this is not going to work. So instead, what we propose is something called layer-wise co-permutation. And what that does is shuffle adjacent layers together. And I have a little demonstration of that here. So consider here the multi-layered neural network, and I lay out the weight matrix of each layer side by side. And then, well, it's side by side and then going top, so it looks like a snake really. And what you do is permute the concatenation of the two adjacent matrices. So let's call the first one WAB and the second one is WBC. It's stored in a transpose manner, so it's WBC transpose. So what we would do is concat of WAB, WBC transpose, and then apply the k-means permutation algorithm on that. What that really does is, graphically speaking, it shuffles the neurons, and shuffling this set of neurons labeled 1 affects the weights on both the left and the right. So that's what we are exactly doing by permuting the rows of the adjacent layers. And we would do a transpose, or think of it as permuting the columns instead of the rows. And here we change the concatenation. As you can see, now WAB is permuted in isolation, but WBC transpose is permuted with WCD instead of WAB as was in the last iteration. So now we do this. So we repeat this until convergence. We do this concat and then transposition and permutation. So the end result of this is we only need one PI and one PO permutation layers just at the input and output. And if you have a sufficiently deep network, then the PI and PO don't really matter. The time cost of that is insignificant compared to the time cost of running the actual layers. So that was solving the problem with fully connected layers. And then we also extended it to convolution layers. Here, the algorithm becomes more nuanced because the conv2D layer consists of 4D filters. But the idea is similar. We were permuting neurons in the fully connected layer case. Now we're going to permute channels. So it is a similar co-permutation algorithm, but we have to just change the way we define a transpose. So in the fully connected layer case, the transpose is a simple transpose on a matrix. But here, what we do is going to be a different kind of transpose, and I show it here. So here's the original convolution layer with an example set of filters. So first, we would reshape it to a 2D matrix with the dimensions being C out times C in, which is the number of output channels times the number of input channels. And then we would do what we call as a column group-wise transposition. So we transpose each submatrix within this large matrix. So we don't transpose the whole thing at once. So you can see that the C out times C in submatrix within this large matrix is transposed. So that's the only change to the algorithm shown on the previous slide, just that the transpose definition is changing for conv2D case compared to the FC layers case. And with that, we can cover CNNs. Therefore, that covers a large segment of practical machine learning algorithms. Okay, so now we'll talk about the pruning schemes in more detail. So there's a bunch of experiments we did with different kinds of pruning and packing, and even within pruning, trying out different techniques from the plaintext world. So the details are in a paper that is going to appear in SORISCs. But for now, I'll just keep it at a high level. So there are several schemes. The first one is the baselines, where you just train the network, prune it, and then retrain after pruning, and then pack it. That's the complete baseline. And then there are different variations. I'll talk about P2T a bit later. P3 is train, prune, and then permute, retrain, and pack. So this is what I just explained over the past few slides. Now P3E is adding an expand step. And the reason is, so after you permute, you still have certain tiles with few non-zeros and few zeros. So these zeros are the zeros that we cannot recover. We cannot exploit them once they're encrypted. So what we're going to do is expand them back. So we're going to undo those zeros. So it's undoing the pruning for those tiles that have non-zeros with zeros. So that step we call as expand. And after expansion, we can retrain again. So that is P3E. So P4 and P4E just introduce a step called prune pack. It's a pruning aware packing step. It's reducing the tiles that contain mostly zeros. So let's say you have a tile with 99% zeros, but 1% non-zeros. So it's going to prune those away. So there's a threshold value, and if there are any tiles with more than threshold number of zeros, then you're going to prune them away. So that's P4E. It's experimentally our best performing scheme. And then now I'll talk about P2T. P2T is a tile-based pruning scheme. So the idea here is we pick a tile shape and we split every tensor into tiles. And then for each tile, we compute the minimum, maximum, average metric of its absolute values, the weight values. And then we rank them according to this metric. And then we prune away the tiles with the lowest value of the metric. So it's taking a very coarse-grained pruning approach in this P2T scheme. And it's really an adaptation of the state-of-the-art scheme at the time of this writing, which is called Hunter. It's just linked here. And this is our baseline for comparison. Okay, so putting everything together, P4E looks like this. So you have the multi-layered neural network here, and the weight matrices are shown here. We first do a prune. So pruning increases the number of zero tiles, maybe reduces the accuracy a bit because you pruned away some values. Permutation increases the number of zero tiles, does not affect accuracy because it's just reordering the neurons. It's not affecting the functionality. Then the prune pack step I explained, it prunes away tiles with just a few non-zeros. So here there was one non-zero, so we pruned this away, for example. So it increases the number of zero tiles, reduces accuracy a bit. And then expand. Expand does not change the number of zero tiles, but increases accuracy. So these are the steps involved in P4E. And in this particular example, in the beginning, we did 61% pruning. We applied 61% pruning. And just after the prune step, we were only able to reduce 10% of the tiles. So the tile sparsity is 10%, but the actual sparsity was 61%. With permutation, the tile sparsity improved to 35%. And after prune pack, it further improved to 45%. And then we did expand to recover back the accuracy. And this is the set of steps we're going to apply for the larger applications that I'm going to show. Okay, so the threat model that we considered is a simple two-party threat model. So there's a data owner with a pre-trained model and private data samples. And he or she is just using the cloud server to run HE inference as a service. We can extend this to three-party or multi-party models, but we have to also do a privacy analysis. But for the two-party threat model, the only additional thing that the cloud learns with our scheme is that there are certain tiles that are pruned away. So it's only learning changes to the structure of the network. But just to remind ourselves, the server would already know the structure in the first place because it knows the number of tiles in each layer. It knows the number of layers, even though it does not know the values of the layers themselves. So the only additional thing it learns is, okay, some of the tiles are not present anymore. So it does not really compromise on the privacy beyond the assumptions in FHE. In addition, we assume things like TLS 1.3 secure protocol for inter-party communication, computationally bounded and semi-honest adversaries. And we note that the semantic security of the HE scheme is not affected at all because the data arrangement and everything we do is before encryption. So it does not affect what happens after encryption. And then the experiments are done with 128-bit security. Okay, so we evaluate our methods on 4 applications. The first one is an MLP or multi-layer perceptron-based classifier. For classifying images. There's another classifier which is based on CNNs. And then we also evaluate autoencoders. There's an autoencoder for image compression. And we also evaluate one for image denoising. So these are the 4 applications. And in addition, we have results for a large HE-friendly AlexNet network trained with trainable activation functions from our prior work. Just to show that we can also support very deep networks. And we consider these data sets as shown. The accuracy measurements and pruning is done on PyTorch. And we integrate the changes that we proposed in HE-layers. So HE-layers is the framework that executes the network in FHE mode. So what we really did is we add a flag to each ciphertext message saying whether it's a 0 ciphertext or not. And if HE-layers encounters a 0 ciphertext, it just doesn't consider it. It doesn't do any computation with it. And internally, it's not stored. So it doesn't consume any memory. And the end-to-end memory and latency results will show are with this parameter. So 8 threads averaging 10 runs. And we used sealed CKKS with 128-bit security and n equal to 32K. Okay. So as I mentioned, P2T is our baseline. And then these show the details of the exact pruning that we did. So it's like local scope, and T average is the average as the metric for ranking the tiles and so on. And then the different charts show different tile shapes. Now, if we recall back, the tiles are 3-dimensional tiles, and the Z dimension is the replicated dimension. So the smaller tiles have a larger amount of replication, and then the larger tiles have a smaller amount of replication. So the best pruning technique we have for CNNs is using P3 for convolutionless and P4E for fully connected with this specific scheme. So it's a lot of detail, but we can ignore it for now. But the results show the trends here. So the x-axis is the amount of tile sparsity we get for a certain amount of applied pruning. And then the test accuracy is the overall end-to-end accuracy of the neural network. So as we increase the tile sparsity, obviously there's a point at which the accuracy tanks. And the markers that are shown here show the point at which we get the highest tile sparsity for at most 2.5% worse accuracy compared to the original unpruned neural network. So that's kind of, we're assuming that's a point that a designer would like to choose if they don't want to compromise on accuracy, but still want the speed and storage, the benefits with the pruning scheme. So overall, we get 75 to 84% tile sparsity. And across the other 4 applications, averaging over them, we get 48, 57, and 104 for the different tile sizes. The trend there is that the P2T scheme gets actually worse with larger tile sizes. And that's because if you think about it, the larger the tiles, the more the probability that the tile contains lots of important weights along with unimportant weights. And we are doing a blanket pruning on the entire tile. So it is going to wipe out some important weights along with the unimportant weights. Versus with our proposal, we are doing a much more fine-grained and careful pruning. So we are not going to compromise on accuracy that way. And that's where the benefits come from. In terms of end-to-end latency and memory, and that because that's what ultimately matters, the results are shown here. So this is for the AED noise replication on C410. The y-axis is showing the test loss, so lower is better, and then the x-axis is the normalized latency. It is normalized to the running time of the unpruned neural network. So the rightmost point is the best. So for different tile shapes, we get different ranges of improvements, but the reductions range in 10 to 35% and 70 to 35% for memory and latency respectively. Again, within the 2.5% degradation threshold, because we don't want to compromise on the accuracy too much. We can see that the benefits are greater for smaller tile shapes. So 8x8 gives us the lowest normalized latency shown with the marker here. But as I mentioned before, yes, we can go for lower tile sizes. That will give us the best benefits, but we also need to consider the replicated dimension. So there's going to be a lot more replications for the 8x8 case compared to the 64x64 case. And so you need a much larger batch of images, for example, to be used with this model. Otherwise, you're just going to be wasting storage. So if you have if you have such a large batch, you can always pick the smaller tile shapes. But ultimately, what tile shape you pick is orthogonal to our work. It is really dependent on other metrics, like whether the goal is to minimize for latency, memory throughput, and what is the batch size, and other criteria like that. Then we further looked at how many operations we're removing. So by removing the tiles, what is the impact on the number of operations? And turns out we reduce 29 to 63% of additions and 53 to 63% of multiplications. The details are in the table here. But I wanted to point back to this chart and show that for this particular point, we actually applied we did a pruning such that the tile sparsity came to be 99%, but the latency is still not linearly reducing with sparsity, and it's kind of saturating. So at this point, there's a 37% latency margin still reduced to be reduced, and we wanted to investigate why that's the case. So it turns out if you do the matrix multiplication with two sparse tensors, the result may be denser than the individual tensors that are used. And these denser results need to still pass through the polynomial activation functions, which we are not reducing. So because we are not doing activation pruning, we are not affecting the polynomial activations. So for that, we need to also consider polynomial activations, which we did not do in this work. So that's just a side note from our results. Finally, just wanted to isolate what is the value of permutation in this grand scheme of things. So for that, we plot a couple of histograms. The histogram is shown here. We're really zooming into the last 86 to 100% the range. And we're going to look at the histogram after doing P2, so which is the baseline, just prune and pack, and the histogram after the prune, permute, and then pack step. So here we applied, so we did prune out 97.5% of the weights. So there's a Gaussian distribution around 97.5. Look at the green curve here, but the tail is squashed because you cannot have more than 100% zeros. So what we're doing after permutation is set of two steps or two benefits emerge out of it. So the first thing is what really matters is how many tiles have all zeros, as I mentioned in the very beginning of this presentation. So we're increasing that from 3.9% to 9.8%. So that is the number of zero tiles that have all zeros and no non-zeros at all. And there's a secondary effect, which is we are migrating some of the non-zeros that were in the less sparse tiles into higher density tiles. So that's shown by the increase in the value of the histogram at the same x-axis point. So which means that you're saving some weights from getting pruned away, and these are the important weights. So these two effects cumulatively give us good pruning for low accuracy loss. And yeah, I think I'm done. So we conclude this work. So we presented a bunch of techniques with pruning, permutation, expansion, and packing. Particularly, permutation is our novel contribution. We described how it operates in a non-client aided HE use case with the framework called HE layers. And we compared against a technique called Hunter and showed benefits in terms of neural network accuracy and fraction of ciphertext eliminated. And we showed a bunch of PPML applications with different data sets to show that we can support a wide set of applications with this set of steps. And that's it. I'm done and take any questions.